All right. We have reached the last item on our agenda. I feel like the day has flown by. We are now getting to our poster session. And I will quickly go over some of the logistics so that you guys know how to participate. So the poster sessions will start in a few minutes, and we will have a bunch of live presentations and some recorded presentations, and we will be streaming them here live on Zoom and on YouTube. Given the time constraints, we will not take any questions from the audience, but please keep the questions coming on the following channels. So you can find the posters on the official CVPR website. There's a dedicated CVPR website for our workshop that has all the posters. Each poster has a dedicated page that contains slides and a 1-minute video presentation. You need a valid CVPR registration to access the content. And you can use the comment section to ask questions. You can find the full posters, the papers, on our own workshop website. We will not be including the papers on the official CVPR website, but you can find all the materials, all the content on our workshop website. That is your one-stop shop. Feel free to discuss the posters on Slack. You are invited to the Slack channels, and each poster has a dedicated Slack channel for discussions, and the authors will be hanging out in the Slack channels to answer questions. We have a bunch of live poster spotlights now, and I think the authors are getting ready to give the presentations. Once we have given those presentations, we will continue with the recorded videos, and then please ask your questions and discuss the topics on Slack and on the CVPR website. And with that, I think we can start with our first presentation. You can take a look at the workshop website, browse through the papers, get some impressions from the live presentations, and then mingle with the authors in the Slack channels.
So hi everyone, I'm Cho-Ying, and today I'm going to present my work, Geometry-aware instance segmentation with disparity maps. This work is done when I was doing my internship at Argo AI. And our contribution of this work is mainly focusing on, we perform the instance segmentations with geometric information using disparity maps and do a sensor fusion to combine geometric information and images. And we also collect another high quality driving stereo data set, which have 4 times larger if multiplied by B that compared to the current best cityscapes data set. And the lower shows our teaser result compared with MassRCN. And our purpose of this work is to do the sensor fusion work of incorporating geometry information and images information. So instance segmentation on images will be affected by the textures overlapping areas of different instances and or different lighting conditions. And instance segmentation by depth or disparity maps, since it's a dense map, is limited by its measuring distance of sensors. And so the advantage of our work is to try to incorporate the geometric information to suppress false predictions by MassRCN or methods only on images. And if directly incorporating information from images and geometry information, we will face a dilemma that since there are information imbalance on images and dense maps, such as if there is a car at long range, then it will be hard to and that car is uncaptured by the depth sensor, but it's captured, but it's seen in images. So if directly doing the sensor fusion to incorporate these two images, the depth map or disparity map and the images, it will fall into information ambiguity that the network would not know if there is a car or not. So compare with, so to try to resolve this issue, so we propose to use a long range focal length and long range long baseline on the stereo cameras that follows the relationship in the far at the lower side. And our method is shown here, is our whole pipeline. So for gaze, our method is called GazeNet. So our GazeNet first takes in a left frame image as a primary frame, and with associated disparity maps, that disparity map is generated from another disparity map estimation network called PSMNet as a state-of-the-art network to do that task. And we utilize this network to inference the disparity map of the corresponding left images. And we use the, as done in MaxRCN, and they use the bounding box head and max head to crop the 2D ROI. And we also do that on the disparity map to crop the 2.5D ROI. And we next to back project this disparity map onto the 3D space. So we create or formulate the 3D ROI here. And by sampling, we use, and after sampling, we use a point cloud based instance segmentation network, so a point net network, to regress the instance on images. When we also use the image-based instance segmentation network to do image-based instance segmentation network is basically a CNN to regress the maps of 2.5D. And we also do another job to regress the max IOU. So here we summarize our representations here. We use the 2D images, 2.5D disparity maps, and 3D pseudo LiDAR representation with a point net structure to do the instance segmentation. And we also do another that use the max IOU head to, that is a scoring-based method to regress the scores of each mask that represent the quality of each mask. At inference time, we try to incorporate this regress mask, since we have three kinds of representations, 2D, 2.5D, and 3D representations. At inference time, we want to fuse these masks together to get the final mask. So we use the scores regress from the max IO head to incorporate these masks together into a last mask. So first we have the 2D and 2.5D and 3D masks. We fuse the 2D and 3D masks first, since they are from the same source. And then we fuse the 2D and fuse the 2D mask and disparity mask together to get the last final mask output. So the advantage is that the lower quality masks will be suppressed by the lower scores here, and the final predictions by combining image and geometric mask. These are dataset comparison with other dataset that are presented with the stereo maps, stereo cameras. So here we mainly compare to the cityscapes here, and this shows the sensing range of cityscapes in our HQDS dataset. Cityscape is corresponding about 50 meters long, and our HQDS dataset it has a measuring ranges about 150 meters with our validated with our GPS information here. And here we show a result that use our HQDS dataset with our GazeNet network. So we compare with other state-of-the-art works that mainly validated on the COCO dataset, and we use their public release codes to run on our HQDS dataset. So basically, we compare with MaxRCN and the MaxRCN, and using the Cascade backbone network and HTC, and this is our GazeNet result. So you can see that our GazeNet result outperforms MaxRCN by a large gap on both bounding box evaluation and mask evaluation. And we also compare massive or CNN with different kinds of backbones. So the backbone we'll compare with are using ResNet 50, ResNet 101, and ResNext 101 here. And the next comparison is on cityscapes. So we also compare our results and validate our method on cityscape server here, and only compare to the original mass or CNN method. And this shows our final results qualitatively with a regress disparity map and our case net segmental ground and the ground truth and the instance segmentation result by other related works. So thank you, and this is our project site, and we are from USC and Ratle, and thank you very much for listening to this presentation.
All right, hello everyone. My name is Frédéric, and I'm going to present you some work I've carried out with my colleagues Martine and Loïc. We're part of the R&D group at Samasource, and our paper is about human-centric efficiency improvement in image annotation for autonomous driving. So what we're presenting here is a study of our integration of a few-click annotation tool in a production environment. So image annotation, as you know, especially instance semantic segmentation, is very time consuming, and there have been many machine learning based methods to speed up that process. For example, Dexter and a variety of other methods. However, these aren't typically tested in a production environment in the literature where we really desire a high quality, so IOUs of 95% and more. Also, the output of the machine learning models needs to be easily edited by human annotators, and very often this is not a perspective that we have in research papers that are purely based on accuracy metrics. So I'm going to briefly present you our system, our few-click annotation approach. So the images that we're looking at here are from the Cynthia synthetic automotive dataset. We chose that dataset for our study because while it has instance masks for instance, and we focused on the problem of instance segmentation, it also has a good diversity of scenes, and the synthetic data allows us to have the exact ground truth to compare annotation methods. Now, the Dexter approach is a little bit the foundation of our model here. It relies on the fact that the annotator will input 4 extreme clicks at the top, bottom, left, and right of the object. In order to produce a crop, we'll produce a heat map from those 4 clicks, concatenate it with the image, and feed that to a segmentation model. In our case, we've used our own custom segmentation model here. Now, Dexter will output a raster mask. Now, in order to make this more editable by human annotators, we've also introduced a raster to polygon vectorization algorithm. Now, that algorithm, I'm going to say a few words about how it works here. Basically, we take the raster mask. We use a Gaussian kernel to just smooth the boundary. We then found the contour C using the marching squares algorithm, which is a common algorithm in the graphics literature. The problem here is that what it will output is a relatively uniform distribution of points on the boundary. So what we did next is to sparsify that contour using a criterion based on local curvature. In a nutshell, we really want to grab the points where the curvature is high and where humans are more likely to want to make edits to those points. And this yields at the output a polygon. We carried out a couple of A/B testing experiments using annotators in our own data delivery centers. So we have a platform, an annotation platform here, the Sama Hub. We ran a first comparison comparing manual annotation with our few-click approach. Now, this may seem obvious, but in our experience, it can happen that sometimes making edits to a pre-annotation can be as long as annotating from scratch. So we just wanted to validate the efficiency gains brought about by the tool. Then we run a second experiment, which is more of a usability study on few-click annotation. What we wanted to measure is, we wanted to assess whether having the annotators produce an input to the machine learning model provided more confidence in the output of the model. So in other words, were they more or less likely to edit the prediction if they contributed something to that prediction. So we run those two experiments using a pool of annotators. We obtained some results that are portrayed here on this slide. So the first experiments, few click versus manual. So similar to what has been observed in the literature, we've obtained a 3 to 4-fold gain in terms of total annotation time. So that comprises annotation, adjustments, and everything else. So you can see the box plot on the right. And the IOU is very similar. It's in the 95, 96 range. They're not statistically different. The second experiment is less, the result is less dramatic, but it provides some hint into the notion that perhaps having an interaction between the human annotator and the machine learning model provides better confidence into the prediction of the model, because here, when the annotator is presented with a pre-annotation, they seem to tend to adjust it a little bit more. So this is a research area that will focus more in the future, but it's a very interesting result, we thought. Now here I'm just giving a few examples of model output versus manual annotation. So the quality is very similar, and you can see that the polygons are natural and realistic, and they're sparse enough to be easily edited by an annotator. So this has been key in obtaining those results. And that concludes my presentation. Thank you very much.
Hello, everyone. My name is Noor. I work here on the perception team at Zoox. And today I'm going to be presenting to you some of the work that we've done here at Zoox. The title of our work is Fishing Net. And in this work, we propose a supervised end-to-end approach to predict from multimodal sensor data the short-term future states of the world for autonomous driving. This work is mainly motivated by two important systems for autonomous driving. One is perception, and two is prediction. The perception system is typically tasked to build a representation of the current state of the world that encodes the geometry and the semantics of the scene. And then this representation is fed into a prediction system, which is tasked to predict the possible future states of the world. The perception system typically consumes multiple sensory data from multiple modalities, fuses all of the information to output one coherent representation. These sensors include LiDAR, radar, and cameras or vision. Having two separate systems, each with their own set of neural networks, can increase system latency and system complexity, which led us to ask the following research question. Can we unify both perception and prediction into one end-to-end module and still predict a representation of the world that is interpretable and can be consumed by a downstream motion planning system? So we formulated the problem as follows. Given a sequence of sensory data from multiple modalities, predict a sequence of top-down semantic grids. The reason we chose the top-down representation is because concisely encodes the geometry and the semantics of the scene, and it is also independent from any sensory reference frame. And it also facilitates the task of letter fusion, as we shall see. Here I show more in detail our top-down semantic grid. We encode three semantic classes. One is vehicles, shown in green, and then vulnerable road users, which include pedestrians, bicyclists, and motorcyclists, shown in red, and then finally background. As for the source of our ground truth, we leverage our main perception system's 3D bounding box outputs, which gives us access to large amount of data for model training, basically free ground truth. And we also evaluate on new scenes of lift data sets, which are smaller in size, and we also achieve good performance. So here I'm going to describe the overall architecture of our pipeline. So we temporally aggregate sensory data from three sensors, LiDAR, radar, and vision. And then the sequence of sensory data goes through its own convolution neural network, which then predicts a sequence of top-down semantic grids. These grids are then fed into one fusion block to output one coherent representation of the state of the world at the current time step and into the future. This framework has multiple advantages. One, we have an intermediate interpreter representation for each sensor modality, which allows you to reason and debug any system failure, and also reason about each modality's failure modes. And two, each modality has its own neural network, which allows us to run inference in parallel, and then synchronize in the output, which gives us the ability to reduce system latency a lot. So in terms of fusion, here we evaluate using two different fusion mechanisms. One is average pooling, basically computing the average of all the output top-down semantic grids, and the other is Asian-based priority pooling. For the LiDAR and radar neural networks, we compute a set of grid-based features. More details are described in the paper, and build a top-down image view of the point cloud transformed at the robot reference frame at the current time step. This is to implicitly encode the ego motion compensation, which facilitates the task of prediction for each neural network. As for vision, the problem is slightly different because we're consuming the image data from the perspective view of the camera. So in order to account for the geometric transformation from the pixel space to the top-down space, we have an additional layer in the middle, the encoder and decoder. And this layer consists of a sequence of fully connected layers, one sequence per camera view. So here we consume 6 camera views. So we had 6 branches, each consisting of a set of fully connected layers. These layers effectively learn a transformation from the pixel space to the top-down space. It was mainly inspired by an approach done in cross-use semantic segmentation, and we extended to also do future prediction. So here I show the results. We evaluated and see 3 large data sets. One is our purpose-built data set that we collect internally, which consists of approximately 2 million training samples. And we also evaluate on new scenes of lift. Across the board, the LiDAR modality was achieving the best results compared to other modalities, and that's because it had higher resolution compared to radar, and also the input was already in top-down and ego motion compensated, unlike vision. We also found that our pipeline performs well in terms of the modalities and also the fusion outputs with the vehicle and the background class, but we struggle a little bit with the VRU, the vulnerable road users class, with the pedestrian class. And this is mainly was due to the sparsity of that class compared to any other classes in the top-down representation. And the way we compensated for this is by adding an extra multiplying factor in our loss function. So here I show some qualitative results of all the model's outputs. What we found interesting with this approach is that it was able to infer different types of motion dynamics. So we can see it was doing pretty good on the static objects right here. And it also was able to infer different types of motion, including linear motion and more complicated motion, such as turns and motion that basically has more yaw dynamics. And then finally, I would like to show you a video of the whole system running. On the left, you can see the inputs, and on the right, you can see the outputs. The top row is the current time step. The subsequent rows on the left are showing the history, and the subsequent rows on the right are showing the predicted frames by the models. And then this concludes my presentation. Thank you all for your attention.
Cool. Hi, my name is CK, and I'm an undergrad researcher from UC Berkeley. I work with my colleague Kahan and supervised by Professor Joey Gonzalez. Today, I'll be presenting my work on bird-size segmentation. So the task of bird-size segmentation takes as input n RGB side images from different angles and produces output of semantic segmentation on the bird's eye view representation of the world. And this representation not only contains cars, pedestrian, but it also contains road lanes, trees, drivable regions, and buildings. In the interest of time, I'll skip a few slides here, but they're left here for completeness. There are 2 main challenges to this task. The first challenge is how do we transfer from side view to bird's eye view? And the second challenge is because this ground truth is very difficult to collect in the real world, how do we train in a simulator? A question is then, how do we train from a simulator and then transfer learning to a target domain? Our pipeline, our perception pipeline focused primarily on solving these 2 challenges. And here is a diagram of our pipeline. We see on the top here is our training protocol in the source domain, and bottom here is the transfer learning protocol for the target domain. We split our pipeline into 2 phases, with phase 1 depicted here and phase 2 here, and we use an intermediate representation that bridges the 2. First, let's talk about the source domain training. So our pipeline takes in RGB image images and run semantic segmentation and depth estimation on each of them to produce segmentation maps and depth maps. We then combine the two into a semantic point cloud, which we project onto a rasterized version, rasterized image. This is our intermediate representation, which we feed into our phase 2 model, which is yet another CNN model, and to recover the full birth size segmentation. An advantage of this approach is that we're able to provide much stronger depth training signal, because in this depth estimation pathway, we're able to provide ground truth LiDAR points as supervision. In addition, because we predict pixel-wise depths, we're able to project them onto the 3D world using pinhole camera model and to use geometry to more accurately connect semantics from the image feed plane onto the bird's eye plane. Next, let's talk about transfer learning. Our transfer learning protocol works as follows. For phase 1, we fine-tune our model using target domain data. The phase 1 model includes the size segmentation as well as the size depth estimation. And for phase 2, where ground truth is not readily available, we use our source domain model as is on this target domain. And the reason we're able to do this is because our intermediate representation abstracts away some of the domain invariant features and allow our models to be deployed as is. To elaborate, here's our pipeline, a simplified version of our pipeline. In phase 1, depicted here, even though going from RGB to projective semantic point cloud, even though there's a domain gap in the RGB images, because we're able to contain this kind of data in any target domain, we're then able to fine-tune the whole phase 1 model. And in phase 2, while we are unable to collect this kind of data, this kind of ground truth, because our intermediate representation abstracts away features such that are variants across domains, such as brightness, building appearance, and preserve the common features, we're able to apply the source domain model as is. We evaluate our method on a dataset we collected in the Carla simulator. We collected 14,000 frames in 6 towns and 2 weather conditions. Some of the results on the source domain, we observed that for the MIOU on the source domain, we observed a 14% improvement over the baseline. And if we were to supply both models, ours and the baseline, with ground truth depth maps, we further see this performance gap increase even further. And for transfer learning results, we train both models on the source domain and evaluate on the target domain with respective transfer learning protocol. We observe that the performance gap still exists, and our method still outperforms the baseline. For some qualitative results, we see that our method produced much more fine-grained prediction over the baseline. And for certain rare class, such as road lanes and stop signs, we're able to predict them, whereas the baseline completely misses them. This is all I have for today. I want to thank Waymo for this amazing opportunity. Thank you so much.
Hello, my name is Matthew O'Kelly. Today, I'm here to present my work entitled Efficient Black Box Assessment of Autonomous Vehicle Safety. This work is a collaboration with my colleagues, Aman Sinha and Jessica Noureldin at Trustworthy AI. I'll begin by telling you about a problem faced by autonomous vehicles, which Alex, Ratle, and many others today have highlighted. The issue is that there's no generally accepted method to quantify and bound the risk that an AV poses to its passengers and other traffic participants. Maybe this doesn't sound that hard, but the problem needs some more context. Despite popular sentiment, human drivers are on average extremely safe drivers. AVs aren't going to be compared to teenagers or impaired operators. In fact, human drivers are so good that serious accidents occur on the order of once every 100 million miles, according to a recent report by RAND Corporation. This means that we would need to test tens of billions of miles to accurately capture and compare the performance of AVs relative to human drivers, Even if you're Google and you own a data center, this is going to be expensive and slow. Our solution is based on a field of statistics known as rare event simulation. We begin by concretizing the estimation problem. Our goal is to find value P gamma, which is the probability of a dangerous event, or in this case, a crash. Our method utilizes 3 ingredients. The first ingredient is a generative model of the world. We'll call this P0. It's the base distribution that describes the behavior of other traffic, the weather, and road conditions. Once we've defined P0, we need a safety metric, f of x, which maps trajectories of the system to a score. In our case, you could consider something like the minimum time to collision over a rollout. The time to collision is greater than 0, there's been no crash. The smaller it is, the more dangerous the rollout. Given the safety metric, we also need a safety threshold, which defines a minimum acceptable value of f of x. Practically speaking, this might be 0.5 to 1 second. Since P gamma is small, it'll be hard to sample events where f of x is less than gamma. Equivalently, there are very few crashes in our simulations. Our approach is to decompose the rare event simulation problem into a series of non-rare levels. So for example, at level 0, we may take any TTC less than infinity, all simulations. At level k-1, we require that the simulation has a TTC of less than 2.5, and at level k, 1.5, all the way until we reach the value of gamma. Consider this toy problem. We're interested in knowing the probability that both coordinates of a random variable drawn from a 2D standard normal distribution are greater than 6, corresponding to the pink region of interest on the top right. If we look at the samples xi drawn from P0 in blue, you'll see that some are closer to the region of interest than others, and we can see what the level set looks like. It's this dashed line level set of f of x. In our method, we adaptively choose the levels as the simulations proceed. At each iteration of our method, we will discard a portion of samples delta and rejuvenate them by drawing independent replacement samples that lie above the previous intermediate level. Pictorially, this looks like this ladder of colored samples that you can see on the right. For this toy problem, it's interesting that the true probability of reaching the region of interest is 0.97 times 10 to the minus 18th. Our method is able to compute an estimate of this probability as 1 plus or minus 0.11 times 10 to the minus 18th with only 1 million function evaluations. Since this is a workshop on autonomous driving, not statistics, let's see how this method works in the context of the original goal, scalable AV safety assessment. For our paper, we created a minimally invasive fork of Comma AI's OpenPilot, which interacts with the Carla autonomous driving simulator. Note that our approach is independent of the simulation environment chosen or the vehicle model under consideration. We chose these components because they're open source and we can freely share our results. OpenPilot is a user-installed dash cam, which utilizes a relatively conventional stack, which includes both machine learning components, such as PoseNet for ego vehicle motion estimation and transformations of features in image space back to 3D, as well as two model predictive controllers for maintaining the ego vehicle's lateral and longitudinal position within the lane. In our experiments, we search over the weather, sun position, behaviors of other vehicles, as well as their positions and velocities. The safety metric we choose is the minimum time to collision over a simulation. In this video, you can see examples of many instances drawn from the base distribution, all of them not crashes. In fact, you can watch this for hours. Using our method, we are able to identify non-trivial failures of the OpenPilot system. In this video example, neither the MPC nor the perception system explicitly fail. As you can see, the perception system is blinded by the sun and has a lens flare, leading it to predict in the bird's eye view that it's rather uncertain about the lead vehicle's position. On the other hand, the MPC is auto-generated code, which plans given the estimated pose of the lead vehicle, what it believes to be a safe trajectory relative to its knowledge of the world. This failure is actually at the interface of the two systems. The MPC treats the uncertainty of the estimated pose by examining the mean value of this yellow set, causing it to believe that the lead vehicle is further forward in the world than it actually is. In conclusion, our method is able to reduce the variance of estimate of p hat gamma by 100x relative to naive Monte Carlo methods compared under the same computational budget. It's available to try at our GitHub link, and you can learn more at our website, trustworthy.ai. Thank you.
Thank you for the great presentations. So the remaining presentations have been pre-recorded, and we're going to play back those recordings now. Please feel free to join our Slack channels now and start discussing all the presented work. This concludes the presentation part of our workshop. Let's thank all the speakers again. And I would also like to thank everyone who joined us today. Enjoy the discussions on Slack. Thank you.
Hello everyone, my name is Juana Valeria Hurtado. I'm a PhD student in the Robot Learning Lab at Freiburg University, and today I'm going to present our work named Multi-Object Panoptic Tracking. Comprehensive understanding of dynamic scenes is a critical task for intelligent robots to autonomously operate in their environments. This is a challenge that requires tackling multiple tasks simultaneously to detect, localize, and identify the scene elements, as well as to understand the current context, dynamics, and relationships. Research in this domain has been mainly focused on addressing a specific task individually, and as most of these tasks are required to be performed simultaneously in real-world applications, the scalability of employing several individual models is becoming a limiting factor. This also introduces additional complexities since the overall performance depends on the capabilities of the individual networks. We introduce a new perception task that we name Multi-Object Panoptic Tracking. The goal of this task is to encourage holistic modeling of dynamic scenes by tackling multiple problems that are typically addressed disjointly. We incorporate semantic segmentation, instance segmentation, and multi-object tracking. We also propose the Panoptic TrackNet architecture, a single end-to-end learning model that addresses the proposed MOPT task. We build upon the recently introduced state-of-the-art efficient PS architecture for panoptic segmentation. We employ a novel sharp backbone based on efficient B5 topology with a two-way feature primate network. We use three task-specific heads that simultaneously perform semantic segmentation, instance segmentation, and multi-object tracking. Finally, we adaptively fuse the task-specific outputs from each of the heads in our fusion module to yield panoptic segmentation output with temporally tracked instances. In order to facilitate quantitative performance evaluations of MOPT, we use the standard panoptic quality PQ metric that is used to measure the performance of panoptic segmentation, and we adapt it to account for the incorrectly tracked objects in MOPT. To do so, we compute the set of track ID discrepancy, true positive, false positives, and false negatives. Our metric is comprised in three parts. First, the average IOU of matched segments accounts for the correct predictions. Second, the IOU of matched segments with track ID discrepancy penalizes the incorrect track predictions. The third part, which is added into the denominator, penalizes the segments without matches. We also include a less strict version of our metric, SPTQ, that penalizes the track ID errors with an average IOU of matched segments with track ID discrepancy. Finally, since these metrics are calculated for each class individually, we compute the PTQ value averaged by classes. We present results for both vision-based MOPT on Virtual Kitty 2 and LiDAR-based MOPT on Semantic Kitty. To the best of our knowledge, there are no methods thus far that jointly perform semantic segmentation, instance segmentation, and instance tracking. Therefore, we provide several new baselines for MOPT by combining predictions of state-of-the-art task-specific models. On the results of vision-based MOPT, we observe that our proposed Panoptic TrackNet model achieves an SPTQ score of 47.27%, which is an improvement of 0.58% respectively over the best performing baseline. The benefits of our model can be observed in the number of parameters and flops that it consumes, where it's almost twice more efficient than the baselines. Similarly, our Panoptic TrackNet achieves the highest SPTQ score in LiDAR-based MOPT, while being also the fastest in inference time. We can see that our model assigns a color to each TrackThink instances and retains the depicted color temporarily. Here we can see that Panoptic segmentation performs the detection and segmentation of instance-specific thing classes, but instances are not consistent across frames. Multi-object panoptic tracking augments panoptic segmentation with a tracking ID that identifies single instances and is consistent across frames. Thank you for your attention, and for more information, please visit our webpage.
In this work, the focus on unsupervised domain adaptation. Images and annotations are available in the source domain, while only unlabeled images are available for the target domain. We show that alignment of global image characteristics between source and target domains helps to reduce the domain gap. The state-of-the-art methods integrate additional domain adaptation components into the detector architecture for local and global feature alignment. The first proposed method is called feature distribution matching that transforms a source image in such a way that it obtains the color mean and covariance of the target image while retaining the source image content. We also show that histogram matching operation leads to similar results. Histogram matching manipulates pixels of a source image so that its histogram matches that of a target image. The effectiveness of both methods is demonstrated in a variety of domain shifts between well-known public benchmarks. Applying feature distribution and histogram matching results in a significant performance boost compared to detection results without domain adaptation.
Welcome to ESL. Semantic segmentation models are crucial for autonomous driving applications, but require a lot of costly, manually labeled segmentation maps of real-world urban scenes to train in a supervised fashion. To mitigate this need of annotation, unsupervised domain adaptation is a strategy that leverages labeled data from a source domain to adapt the semantic segmentation model to an unlabeled target domain. In order to further improve the performance of existing unsupervised adaptation techniques, pseudo-labeling aims at generating labels from the predictions of a model on the target dataset, which can be used as additional supervision during training. Usually, pseudo-labeling uses the maximum class probability of the prediction as a measure of confidence, and selects pixels whose maximum class probability is above a given threshold. We propose to use the entropy of the pixel prediction as a more reliable measure of confidence, and select pixels whose entropy are below a given threshold. Experiments show that ESL consistently outperforms the usual pseudo-labeling strategy on standard domain adaptation benchmarks. Thank you for watching.
Hello everybody. Let me introduce you with our research topic, Vehicle Re-ID for Surround View Camera System. We are the team from Zoox Technology. This vehicle Re-ID plays an important role in autonomous driving. Existing methods applying in the surveillance situation is not suitable for surround view perceptive system, so we decided to try something new. Let's have a look about our exploration. First of all, we annotated and published a fisheye dataset. As you can see, it brings more difficult challenges. The vehicle in the image is distorted. The distortion rate is varies from position. We put 4 cameras in the front, left, right, and rear of the car to construct the surround view system, and here we only use the 3 of them, except rear. We argue the main challenges in the above scenario and divide the task into 2 aspects, single and multi-camera view. First, let's take a look at a single-camera vehicle Re-ID task. It aims at matching vehicles from the same view in consecutive frames. We optimize the same RPM++ model in the picture on the right. The ROU is replaced by ROUR to adapt the Re-ID task. And the Re-ID pays more attention to center drift than tracking. We adjust the ROU to a centric drift metric and suggest the Re-ID confidence to verify accuracy of Re-ID result. Then, to elevate the box drift caused by occlusion, we introduce the occlusion coefficient. Each object is assigned a single tracker to realize Re-ID in single channel. The outputs are post-processed by the quality evaluation model. For trigger 3, its ID is removed forever after consecutive occluded frames, and for new coming vehicles, we assign them new IDs, just like trigger 4. Then we arrive the vehicle ID in multi-camera. Here we use the BEV-Seg model. Let's look at the picture on the right. The vehicles marked in same color is wrong just to be different cars because of distortion. And in the green box below, the car is decided as same car for the similarity. To overcome the above problems, we introduce the attention mechanism in the local branch, and we get the confidence score S1 from measuring Euclidean distance between this feature and the features stored in the feature gallery. And then we get the score S2 from the projection distance of target to front or rear to key points. The final score of target ID is S. Here I need to mention the multi-camera ID association in this paper is implemented in a certain order. We can see that the red arrow points the targets appear on the right or left side of front camera. Only the right or left camera needs to be associated. When a new target appears on other areas of left or right camera, it just needs to be associated with the front camera. The rest cases only need to be carried out in their own camera. Finally, the experimental results are shown here. We evaluate the results with the identity consistency. It is obvious that updating the tracking tablets with RUR and CR and delete 4 frames of occluded objects, their identity consistency are greatly improved. While examining the strategies together, our strategies in a large improvement can be obtained as shown in the last row. So far, the plan we have adopted has achieved certain results. That's all about our research. Thanks for your listening.
I'm Renzhou from Horizon Robotics. I'm here to introduce our anchor-free one-state point cloud 3D detector. Point cloud 3D detection is important for autonomous driving. Most previous works try to solve it using anchor-based detection methods, which come with 2 drawbacks. First, post-processing is relatively complex. Second, tuning anchor parameters is tricky. We are the first one to address this problem with an anchor-free and NMS-free one-state detector called AFDet. This is the framework of our method. The whole pipeline consists of 3 main modules. They are point cloud encoder, the backbone and next, and the detection head. For detection head, we build 5 subheads. From left to right, they are heatmap prediction, offset regression, z-axis regression, 3D side regression, and orientation regression. We show some preliminary results on Waymo validation set. We can see that our method outperforms the state-of-the-art single-stage method with much less training epochs. We train our model for only 10 epochs, while others train for more than 75 epochs. Here are some visualization results. The first line are some heatmap predictions. Thanks.
With 3D GCK, we propose an extension to object detectors to enable 3D object detection from monocular RGB images. It uses 2D bounding boxes as a basis and estimates key points of the object of interest within this 2D bounding box. These key points are used to lift the detection into 3D space. Due to its design, it is fast and can be universally be applied to any modern 2D object detection framework. 3D GCK follows a 3-step scheme resulting in a 3D 9 degrees of freedom bounding box. First, it estimates an initial 3D bounding box and calculates the corresponding 3D translation. Second, it refines the aspect ratios and the size of the bounding box. Third, the rotation is refined. We evaluated 3D GCK using Kitty and Nucine's benchmarks. Compared to other lifting approaches, 3D GCK achieves comparable results in both 3D average precision and average orientation similarity, and significantly outperforms current state-of-the-art methods in speed.
Hi, this is Jinkyu Kim from UC Berkeley. Humans learn to drive through both practice and theory, for example, by studying the rule, while most self-driving systems are limited to the former. Being able to incorporate human knowledge of typical causal driving behavior should benefit autonomous systems. Here, we propose a new approach that learns vehicle control with the help of human advice. Specifically, Our system learned to summarize its visual observation in natural language and predict an appropriate action response. For example, vehicles should slow down when the road is wet. Our model then predicts the controls accordingly. Moreover, to enhance interpretability of our system, we introduce a fine-grained attention mechanism which results in more interpretable visual explanation by visualizing object-centric attention map. Thank you.
Thank you for listening to our presentation. In this work, we work on sensor fusion of images and geometric information to perform instant segmentation on driving scenarios. We collect our own dataset with high-quality stereo images. Our geometry-aware instant segmentation network, GazeNet, is based on mass RCNN, and we exploit geometric information at ROI heads. We adopt three kinds of representations in our work to regress maps: 2D, 2.5D, 3D pseudo-LiDAR representations. At inference time, these maps are combined using mass scoring and linear combination to fuse maps using their scores. We collect a high-quality driving stereo dataset, and we show a comparison with other datasets here. We show numerical results. Our GazeNet attains the state-of-the-art. This is a visualization of instant segmentation results from GazeNet.
Hi, we're Samasource, and we present you a study where we focus on integrating a few-click segmentation system with human annotators in a production environment where high quality is expected. Our few-click annotation system combines a semantic segmentation model that integrates human annotators' inputs following the Dexter approach, with a clever raster to polygon vectorization algorithm, thus producing annotations that can be easily edited by annotators.
We've set up two experiments, manual versus few-click annotation, and few-click versus simulated few-clicks, the goal being to measure the contribution to adjustment time of having the annotator produce those 4 clicks. Results confirm that the few-click approach improves drawing time while retaining a high IOU. They also confirm our intuition that having annotators take part in the process is preferable to a pre-annotation scenario. The few-click method also produces very realistic polygons compared with the hand-drawn ones. Thank you.